graphs of polynomial functions. So in section 3.2, we talked about what graphs of polynomial functions look like. And we have, a limited ability to really tell what these functions are doing. But there is some information that we can obtain. Okay, given a factored polynomial, we can tell where its x and y intercepts are, and we can tell where the polynomial is positive or negative. So, given a fully factored polynomial, we can find these things out, and then from there, assuming that the graph is smooth and continuous, we can get some idea of what it looks like. All right. By the way, on several people's homeworks in this section and in section 3.6, I see some graphs where people are doing. Well, I mean, I'm kind of exaggerating, but people kind of did something like this. Like this one is kind of ambiguous, but there shouldn't be any sharp corners. All of these functions that we're looking at that are defined by polynomials. So polynomial functions and rational functions, which are quotients of polynomials. The graphs of those functions are all smooth. There's no kinked parts. Right? Nothing like this happens. Okay, so all the curving around should be smooth on these things. Why that is, that's something you'll discuss next semester in calculus. But the graphs should not have any such points. Okay. All right. So, for example, like number 29, maybe let me do one that's an even numbered problem. So in 22, sketch the graph of y equals x times x plus 1 times x minus 1 and 2 minus x. Okay, so, well, the x-intercepts, well, that's where this product is equal to 0. That's either at x equal to 0, negative 1, positive 1, and positive 2. All right, the y-intercept, that's, where x is equal to 0. Let x equal to 0, and then you get, well, 0. All right, so the graph of this function goes through the origin. Other than that, you take your number line, okay, put your x-intercept, minus 1, 0, 1, and 2, and test those intervals to see whether this factored expression is positive or negative. So way down over here, if you take x equal to negative 2, first factor is negative, this one is negative, this one is negative, this one, 2 minus negative 2 becomes 2 plus 2 is 4, it's positive. So in this interval, it's negative. And then with this one, it alternates. Basically because there's no squares in here. When you have, like, you know, some of the factors are squared, then you might not alternate. Okay, but this one alternates. So negative, positive, and then from that you can get, you know, some idea of what this graph looks like. Oh, and also the end behavior of polynomial functions is that they march off to infinity. So here's negative 1, 0, 1, and 2. And we're negative after the negative 1. This is a x-intercept. So it's looking something like that. And it always goes out to infinity towards the end. Either positive infinity or negative infinity. Which one is it? Well, it's, you know, whatever this number line indicates. Okay, so now this is definitely not what it looks like. This is all we can tell at this point. Like, I have the max, we have these local maximums. They're going to have a local maximum here, a local maximum here, a local minimum here. But I made them all about the same y value. And for sure, they're not going to be all about the same y value, nor are they going to occur halfway between the respective x-intercepts. You know, but that's much finer information than what we are able to get with just purely algebraic calculus. Let's take a look. Uh, 2 minus x. Oh, actually, it's I'm not 100% off. Well, you'll notice that the local maximum here at, you know, between negative 1 and 0, it's not in the middle, it's more off toward the left. And this one, it seems to be nice and symmetric around this center line here. And those two guys seem to be at the same y value. Okay, not that we had any reason to believe that. So actually, what our intuition was telling us is pretty much what it is, except for the minimum value. That minimum value is not, it doesn't go down as much as the maximum value does. Right. So these local maximums between negative 1 and 0, and between 1 and 2, they're higher than this minimum is lower. So there's that. And then another one like that, say number 30. By the way, if I took this polynomial, whatever that polynomial is, and I added, like, I mean, I don't know what this value is, but I add like 20 to it or something like that, what's going to happen to the graph? if I added 20 to it, what does it do? It just shifts the whole thing upward 20 units. So all of these points that were x-intercepts are no longer going to be x-intercepts, and if we shifted it upwards, this is no longer the y-axis, then you're going to have x-intercepts just here and here. So just knowing what the x-intercepts are is not necessarily telling you everything you want to know. Because if I added 20 to it and somehow was able to factor it, all I would get would be 2 x-intercepts, and you would know nothing about all this wiggling around that was going on up here. So there's definitely a lot of information that you can miss. So in number 30, for example, we've got, well, say in number 29, I think there's going to be even more missing info there. In number 29, x to the third times x plus 2 times x minus 3 squared. So with this one, x-intercepts are at x equal to 0, minus 2, and 3. Y-intercept, well, it's at y equal to 0, because when you plug in x equal to 0, you get y equal to 0. And then you look at this number line here for positive, negative behavior. So we have minus 2, 0, and 3. So at x equal to minus 3, this is negative, negative, positive. So this is positive. At x equal to minus 1, negative, positive, positive. So it's negative here. 0 to 3, positive, positive, positive. So it's positive here. And then past 3, positive, positive, positive. So it's positive here. But it's 0 there. So, what this information is telling us is the following. So here's 0, negative 2, positive 3, positive, negative, positive, positive. So positive, negative, positive, and then it's got to have a local minimum there because it's got to be 0 here. I shouldn't do that stupid arrow. So there's there's some information that we can get from that. But if you plug this into a graphing calculator or some other type of graphing software, there's going to be quite a bit of detail that we're not getting. So it was x to the third. X plus 2, x minus 3 squared. See, I mean, there's a lot of wiggling around with this one that we just weren't seeing. I mean, in particular, there's an inflection point at 0, right? We went from curved up to curved down. So that's a lot, a lot of detail that we're missing that we just really didn't quite get here. So I mean, here I figured, well, we'll go through the origin like that, but that's actually not what's happening there. What's actually happening is that you have this concave down up to that intercept, and then it's concave up. And that's because it's x to the third. But I mean, why that's going on is is a different story. So what it actually looks like is that. Actually, I could just copy that one. Huh? Okay. All right. So that was in section 3.2. Section 3.3 was on this polynomial division technique, which is just the same as long division of numbers base 10. It's the same idea, and actually it's easier because you don't have any carrying that's going on, like when you do arithmetic base 10 or base 2 or base 16 or whatever base you're using. So say number 20. So we want to divide. So find quotient and remainder. For the division, x to the fourth minus 3x to the third plus x minus 2 over x squared minus 5x plus 1, and rewrite as quotient plus remainder over x squared minus 5x plus 1. Okay, so we want to do this division and rewrite it like this, and the remainder, where the degree of the remainder, right, is less than 2. Right, the degree of the remainder should be less than the degree of the divisor. So we set up the long division in the usual algorithm that we've been using since grade school. And the first term in the quotient, well, I think, well, what do I need to multiply x squared by to get x to the fourth? It's just x squared. So then I multiply x squared by that. So I get x squared, or x to the fourth, minus 5x to the third, plus x squared. And I'm going to subtract this now. Okay. Oh, by the way, when you write this up here, notice that there's a missing term here. There's no x squared. It might be easier for you if you write the missing term in with a 0 coefficient, right? Or just leave it blank right there, like that. But you definitely got to get your powers of x lined up. So I'll just put a 0 x squared, but whatever makes you comfortable. Now I need to subtract this. So to subtract it, I flip the signs. So plus minus plus becomes negative plus negative. And then I add, right? I negate it and then I add it, which amounts to subtracting. So minus 3x third plus 5x to the third, so that's x to the third, and then minus x squared, and then bring down the other terms. All right, so now what do I need to multiply x squared by to get x to the third? Well, just x. So that becomes x to the third minus 5x squared plus x. Right, and now I need to subtract. So plus minus plus becomes minus, plus minus. And then I add. So this one is 0, and then minus x squared plus 5x squared is 4x squared, plus 0 minus 2. And again, you can put in that missing term with a 0 coefficient. Okay, I'm still not done. That's degree 2. And then the degree here is 2. Okay, I want the degree of the remainder to be less than the degree of the divisor. So one more iteration of this division algorithm. So what do I need to multiply x squared by to get 4x squared? Well, plus 4. Okay, so multiply by 4, 4x squared minus 20x plus 4. And then I want to subtract, so I multiply by negative 1. So plus minus plus becomes negative plus negative. This is 0, and I have 20x minus 6. So that's degree 1. So that's my remainder. And this is my quotient. Okay, notice how many iterations did we do of the division algorithm there. This is degree 4. This is degree 2. 4 minus 2 is 2. Okay, add 1 to that and you get 3. That's the maximum number of iterations that you'll need to do. Okay, is degree of the numerator minus degree of the denominator plus 1. And this time we had to do all 3 of those. But whatever, it doesn't always work out that way. So in the end, we get that this is equal to the quotient x to the 4th plus x plus 4, or not x to the 4th, x squared plus x plus 4, x squared plus x plus 4 plus the remainder over the divisor. All right, it's pretty cool, I think. By the way, I mean, we're doing this division of polynomials using the long division algorithm that you learned in grade school, right? So when you multiply polynomials, why don't we do the same multiplication algorithm that you learned in grade school? And for some reason, we don't teach it that way. I don't know why, but you can, right? So it's just a little something extra. This is not, what I'm gonna, hold you responsible for. So side note. So multiplying polynomials can also be done with the grade school algorithm. Right, so for example, so let's multiply x to the 3rd plus 2x squared minus x minus 8 times 3x squared minus x plus 1. All right, so the way we talked about it before, right, was you take every term in the first polynomial and you multiply it by every term in the second polynomial, and then you add all that stuff up, right? It's FOIL on steroids. Right? It's in FOIL, that's what you do. First, outside, inside, last, whatever. It's because it's 2 by 2, you can give them names. Right here, when you want to multiply, you multiply every term in the first by every term in the second, then you add that stuff up. But it's a bit of a mess trying to do it that way. it's easier if you use the grade school method. It's more it's easier because it's more organized. It's the same thing. So write it like this: x to the third x to the third plus 2x squared minus x minus 8 times 3x squared minus x plus 1. And I'm going to multiply that. So 1 times all of this, minus 8 minus x plus 2x squared, and then x to the third. Minus x times this, so that's plus 8x plus x squared plus 2x to the third minus x to the fourth. And again, it's easier because there's no carrying. And then the square. So 3x squared times negative 8, so that's minus 24x squared. And then minus 3x to the third. And then plus 6x to the fourth. And then 3x to the fifth. And now you add all that up. So I don't know if they used to teach you to put a 0 in at each step when you go to the next place. That's where that comes from, because right, when I start with this, so that's 10 to the 0, and then this is 10 to the 1, and then this is 10 squared. So you have to start in the 10 squared spot. So that's where this shifting comes from. It's just lining up these powers of x. Right, and of course, with base 10, these powers of x are powers of 10. The problem with powers of 10, or powers of 2, or powers of 16, for whichever base you use in your number system, binary, decimal, hexadecimal, octal, what's the one for base 3? What's the name? Trinary, I guess. Trinary. You have to do this carrying business. Every time you multiply, if you get something bigger than 10, you got to carry the digit over to the next spot. And that becomes kind of messy bookkeeping, like especially with this. But here, there's no carrying. You just add stuff up. So this is minus 8 plus 7x, and then 2 plus 1 minus 24. So it's minus 21x squared. And then 1 plus 2 minus 3 plus 0x to the third, so I'll just leave it out. Plus 5x to the fourth plus 3x to the fifth. And that's the product right there. Right, it's just that multiplication algorithm from grade school just applied to this situation. So we took this term and I multiplied it by all 4 terms up here. Then I took this term and multiplied it by all 4 terms up here. And then I took this third term and multiplied it by all 4 terms up here. And then, I lined them up in a way to keep the powers of x organized, and then you add up by columns. Yeah. I mean, it's obvious that that's the nice way to do it. The problem with that, I think, is that, it's not done as an inline expression. So here, if you were to do it the way I was talking about, as an inline expression, you can't do this. You'd have to do it off to the side. I don't know why they don't teach it. It's just not taught for some reason. I only just sort of realized it like the first time I taught this course, which was, I don't know, a while ago, but so I only realized this well into my career as a professor of mathematics. Okay. So section 3.4 we didn't do. Section 3.5 is on so when we are concerned with real numbers, with quote-unquote real numbers. Okay, we consider the square root of -1 to be undefined. Okay, however, if you allow it to be a number, or in some context in which we allow it, we call the square root of -1 I. All right, so now, like the square root of -a is the square root of a times the square root of -1 is the square root of a times I. Right, so square roots of negative numbers are no longer a problem anymore. Are no longer an issue. And the fundamental theorem of algebra says that every polynomial of degree n has n roots when allowing for these imaginary numbers. Every polynomial of degree n now has n roots. Not necessarily all distinct. There's this notion of multiplicity. Now has exactly n roots where the imaginary roots come in conjugate pairs. In conjugate pairs. A plus bi and a minus bi. So, for example, number 10, x to the third plus x squared plus x. So find, or not roots, sorry, we call them zeros in this. Find the zeros of x to the third plus x squared plus x, that is, find the solutions to x to the third plus x squared plus x equal to 0. So first we factor as much as we can. Now all of the problems in this text break down into linear factors and quadratic factors that don't factor any further. Well, don't factor any further over the real numbers. So this one doesn't factor. This is linear and that one doesn't factor. Okay, so in this example, we have that x is equal to 0, or x squared plus x plus 1 equals to 0. Okay, and then for the irreducible quadratic, we can solve it using the quadratic formula or completing the square. Oh, I'm sorry, we have time. We have to go. But I do want to mention this real quick because it seems that some folks didn't quite get what we were talking about. So 1 minus 4, so that's -3 over 2. So x is minus 1 plus or minus the square root of negative 3 over 2. And you don't just leave it like that. You call this the square root of 3 times I. Square root of 3 times I. So the square root is given a negative or a positive argument, and then the negative 1 is factored out as this I business. So you have two roots or zeros here. Minus 1/2 plus root 3 over 2i, and minus 1/2 minus root 3 over 2i. So that's a conjugate pair. So, I mean, the quadratic formula, of course, gives you a conjugate pair because it's got this plus minus business there. But that always works out with every polynomial that has some imaginary roots. Okay. All right. So tomorrow we'll go over chapter 4. So that's every. Or no, there's one more. Chapter 3, section 3.6. So we'll do some more review tomorrow. Okay. Come with any questions you have. All right. Have a good day, everyone. I'll be in my WebEx room at 11:30.
Thank you. You too.